Hello, everyone. I'm very excited to have Ian Montague here from Brandeis University. They're going to be telling us about cyber Whitmore K-theory and cyclic group actions on spin-4 manifolds of boundary.
All right, thank you. And thank you to the organizers of GSTGC for an absolutely wonderful conference so far. So today I'm going to be discussing 10/8 types inequalities for spin-4 manifolds of boundary emitting cyclic group actions. Can everyone hear me okay in the back? All right, awesome. So today I'm going to try to fit a 40-minute talk in 25 minutes. So let's go. Oh, okay. So recall the 11/8 conjecture posited by Matsumoto, which says that if W is a closed, indefinite, smooth spin-4 manifold, then B2 of W is greater than or equal to 11/8 times the signature of W. Right? And so this is still an open conjecture, but we have the following result by Furuta, the 10/8 theorem, which almost gets to that. So we have that B2 of W is greater than or equal to 10/8 times the signature of W plus 2. All right, and it's worth noting that these are both sharp for the K3 surface. So like these are both like reasonable inequalities to expect. All right, so without loss of generality, we can assume that the signature is non-positive by reversing the orientation if necessary. We're going to let P be equal to minus the signature over 8, Q be equal to B2 plus of W. And so we rewrite it that way. The 11/8 conjecture is equivalent to the inequality Q is greater than or equal to 3/2 P, and the 10/8 theorem is equivalent to Q is greater than or equal to P plus 1. All right, so what about spin-4 manifolds with boundary? All right, we have the following theorem by Manolescu from 2014, which says that if W is an indefinite spin-4 manifold with boundary, a rational homology 3-sphere, then Q is greater than or equal to P plus 1 minus this correction term kappa of Y, depending on the 3 manifold and the boundary. All right, and so kappa of Y is in general a rational number, and it's defined using the pin2 equivariant K theory of the Seiberg-Witten-Floer spectrum denoted by SWF of Y, which I will go into later, but just something to keep in mind. All right, and one thing to note is that the kappa invariant of S3 with its unique spin structure is equal to 0, and so this recovers Fruta's 10/8 theorem by just scooping out the 4-ball. All right, so one question you can ask is, can we do better if W emits a spin Z mod M action? All right, and so, the answer is yes, otherwise I wouldn't be giving talk today. But what is a spin action? All right, so we gotta be a little bit careful about what's going on here. All right, so let's let M comma S be as either spin-3 or spin-4 manifold. S is the spin structure in question. And let's let tau be a diffeomorphism of order n. All right, if it exists, a spin lift tau hat of tau is defined by the following diagram that you see there. All right, and so, so tau induces a map on the SO3 frame bundle, d tau for free. All right, and then you basically just do a lift to the 2-to-1 cover to the spin bundle. All right, and so what's interesting about these is that spin lifts actually come in 2 flavors. All right, so we call tau hat even if it's still of order m, and tau hat odd if it is of order 2m. All right, so because it's a 2-to-1 cover, sorry, I can't control that. But yeah, so there's like 2 different types of spin lifts. All right, and so the type of spin lifts that you can get depends on the topology of the fixed point set. So one example to keep in mind, let's consider the involution on the 4-ball sitting inside of C2, given by ZW goes to minus Z minus W. All right, so the fixed point set is just the origin, and you can show using a lemma by Atiyah and Bott that this any spin lift of this action must be an even spin lift. So it lifts to an order 2 action. On the other hand, let's take a surface sitting inside of any 4 manifold, closed or with boundary. Consider the double branched cover along that surface, tau, the covering involution. Then any spin lift, if it exists, must be an odd type spin lift. All right, so there's something to keep in mind. Okay, moving on. All right, so we have the following theorem independently by Brian, Fong, and Kim. All right, so let W T tau hat be a closed Z mod 2 to the R equivariant spin 4 manifold with tau hat of either even or odd type. Then we get that Q is greater than or equal to P plus 1 plus R under certain technical conditions, which I'll brush under the rug. All right, so the takeaway is that we get, if we have a 2 to the R fold action, we get an extra R in the inequality, which is kind of nice. All right, and so we have the following theorem. All right, so basically this generalizes to the case of boundary the way you'd expect. All right, so let's W T tau hat as above. All right, the boundary is a Z mod 2 to the R equivariant rational homology 3 sphere. And then you get Q is greater than or equal to P plus 1 plus R minus Manilescu's kappa invariant under certain technical conditions. All right, so that's fine and dandy, but what can we do with it? All right, so before I move on to applications, let me just state some other related theorems. All right, so we'll need some notation for this. So assume we have a Z to the M, Z mod M action on W. All right, I'm going to let B2 plus W sub K denote the dimension of the E to the 2 pi I K over M eigenspace of Z mod M acting on H2 plus. And so in the case where it's an involution, B2 plus splits as B2 plus W0, B2 plus W1, B2 plus 0 is the plus 1 eigenspace, the other one is the minus 1 eigenspace. All right, so now let's restrict now for just odd type involutions. All right, so in 2017, Kato showed that if W is closed, then B2 plus W1, so like the non-trivial part of B2 plus, is greater than or equal to minus the signature over 16. And we have a related result for the case with boundary by Kono, Miyazawa, and Taniguchi from a few months ago. It says that if we have W with boundary, rational homology 3 sphere, then we have the same inequality, but minus the correction term kappa KMT of the equivariant manifold on the boundary, which in general is a different invariant than Manilescu's invariant. Okay. So, all right, we have all these inequalities. Let's play around with them. All right, so I'm gonna kind of organize them on the slide over here. All right, so setup. All right, odd type involution. All right, we get the KMT inequality, Manilescu's inequality, and then our inequality. All right, basically we can do one better than Manilescu's inequality. All right, yeah, there's a lot of hard work too. And actually, you can do a little better sometimes. So I can improve that to a +3 if I assume that the trivial part of B2 plus is even. All right, so this is what we'll be working with. Okay, so let's see this in action. All right, so a nice application of this is to genus bounds in 4 manifolds. All right, so let's K denote a knot in 3 sphere. All right, we define X, sorry, I should have written this down. X is some 4 manifold. A is a homology class in X. All right, we define GXA of K as the minimum genus of a surface inside of X minus a 4 ball whose boundary is K. All right, and so yeah, denoted by that picture over there. All right, so all right, here's the setup. X closed, F a surface inside the punctured manifold. All right, and if it sort of satisfies certain conditions, so if the homology class of F is divisible by 2, F divided by 2 is characteristic, then the double branched cover of this is spin, and the covering involution is a spin action. All right, and so we can use our relative 10/8 inequalities to give us bounds on this genus over here. All right, so I'm going to throw a bunch of inequalities on the board. Don't try to read through all of them. Just get a flavor of what's going on. They look very similar. Some coefficients are slightly different, but what I want you to note is that in front of the signature of K, right, they have a minus 9/16, and in my inequality, we have a positive 6/16. All right, so KMT's inequality is better for negative signature knots, and mine is better for positive signature knots. All right, so they kind of complement each other pretty well. All right, so let's kind of specialize to a special class of knots. All right, let QA be the set of quasi-alternating knots, and SWF spherical to be the set of knots in S3 whose Seiberg-Witten-Floer spectrum of the double-branched cover of K is Helmholtz equivalent to a sphere. Then, if we look at the intersection of these two classes of knots, it includes connected sums of all two bridge knots, for example, and as well as these list of low crossing numbered knots. All right, which is not an exhaustive list, but that's what I know exists in this class. All right, so proposition, if we have a K sitting inside of the intersection of these two classes, then we know what the kappa invariants are. All right, Manilescu's kappa invariant is just minus the signature of K over 8. And Kono Miyazawa Taniguchi's kappa invariant is minus signature over 16. Okay, cool. So, sorry, a lot to say, but I wanted to specialize for this so we can look at these nicer, relatively speaking, inequalities. All right. A lot of similarities. Over here, some things are a little different, and you can see the minus 1/2 in front of there and the positive 1/2 in this inequality. All right, so now I can play around, look in some certain four manifold, certain homology classes. All right, so X is a connect sum of n K3 surfaces. Surfaces homology class 0. We get the following inequalities. All right, and the stars mean under certain technical conditions, which I will brush into the rug. Right. Okay, so fine, we get some inequalities. Get a similar thing for connect sum of two CP2s. Looking nice, right? You can again see the dichotomy. Right, theirs works better for negative signature knots. Ours works better for positive signature knots. And connect sum of n copies of S2 cross S2. All right, we look at this homology class, A1, B1 through A and Bn. All right, the self-intersection number is given by the dot product of A and B, and we can write the inequalities. All right, sound good? Okay, sorry to torture you all, but just some things to keep in mind. We can get slightly better genus counts. All right, so let me say a little bit about where this all comes from. All right, so up there I put the theorem I had before. All right, so this actually all follows from a much more general theorem and construction, which I'll vaguely outline. Okay, so consider the Lie group Can2 is the disjoint union of two circles sitting inside of the unit quaternions SU2. And I'm going to define these two groups. All right, so G even M is pin 2 times Z mod M, and G odd M is going to be pin 2 times Z mod 2 M modulo the diagonal Z2 subgroup. All right, so you can think of these as two different ZM extensions of pin 2. All right, so they're just groups to keep in mind. All right, the idea is that given such a triple and equivariant rational homology 3 sphere, we can construct a G star M equivariant stable homotopy type SWF of Y S sigma hat, where the star is either even or odd depending on the parity of sigma hat, right? Whether it's even or odd. All right, so easier said than done. All right, let's take that for granted. We have our spectrum. All right, how does this go? All right, so first we consider the inclusion of the S1 fixed point set of this spectrum into the whole thing. And take reduced equivariant G star M equivariant K theory of this map that gives you a map going the other way, so the restriction map. And you can check that the S1 fixed point set of any cyber floor spectrum arising from a 3 manifold is actually homotopy equivalent to some representation sphere. And so by equivariant dot periodicity, it's just isomorphic to the representation ring R of G star M. All right, and so what does that tell us? All right, so that means that the image of this map, iota star, is an ideal sitting inside the representation ring of G star M. Cool. All right, so we're going to use that to construct invariants. All right, so before I do that, just to tell you a little bit about the structure of these representation rings. All right, so the representation ring is just the set of virtual complex representations of these Lie groups. All right, with addition and multiplication, how you think. All right, and these are turn out to be Z algebras generated by some variables, W0 to Wn minus 1. And depending on whether star is even or odd, all right, we get some Z variables. In the even case, it goes from Z0 to Zn minus 1. And in the odd case, it goes from Z1 half to Zn minus 1 half. All right, and then modulo some relations, which I will not tell you because they're really gross. But okay, so here's the full setup. All right, what do we do with this? Also, how am I doing the time? Oh, great. Okay. All right, so let's define the set S. It's going to be the set of n tuples of natural numbers such that there exists an element X sitting inside of this ideal, such that if I multiply X by W0, I get this element over here. All right, so it looks a little weird as stated. All right, if X is just that monomial in the Wi's with those powers, all right, then clearly, W0 just moves that up by 1. All right, you can have, but basically this multiplication by W0 kind of collapses these Z variables onto the W variables, right? And so it gives you a nice concrete part of the representation ring to work with, right? And it kind of gives us a sort of semi-infinite lattice inside of n to the n. All right, and we're going to endow n to the m with the partial order, right? K less than or equal to L, if and only if Ki is less than or equal to Li for all I. And then how do we define our equivariant cap invariants? Well, we take it to be the set of local minima of S with respect to this partial order. All right, and so because we're working in n to the m, all right, it's not totally ordered, there might be multiple minima of this set. All right, so this is kind of abstract. Let's just look at some examples. It's nice. Oh wait, sorry, one more slide. Okay, so that's the definition of equivariant cap invariants. All right, just a side note in general, SWF is a formal rational desuspension of a G star M space by representation spheres. I know it's a little weird, but that means that we kind of shift these cap invariants until they lie in Q to the M. But okay, basically the idea goes through. So let's look at some concrete examples here. The 2, 3, 11 B-scoring sphere, the spin structure, and let's look at the involution, which realizes it as the double branch cover of Montesino spot. All right, it turns out that the set S, all right, is given by this kind of shifted quadrant shaded in purple over there. All right, and the cap invariant is just that unique point sitting in the lower left-hand corner. All right, so it's kind of nice to visualize these guys in this way. All right, let's look at the same manifold with a different evolution, which this is the evolution that realizes it as the double branch cover of the 311 torus knot. All right, and so we kind of get two off kilter quadrants, all right, and we get two local minima 0, 1 and 1, 0. All right, and so in particular, this can kind of see the difference between these two evolutions, which is kind of nice. Okay, so that being said, all right, here's the actual full general theorem that I have, right? So for all n, all right, but W be a Z mod M equivariant filling of Y, and Y rational homology 3-sphere. All right, I'm gonna let Q be the vector. I don't know why there's brackets. It should be parentheses, right? It's like the equivariant decomposition of B2 plus, right? Sitting inside of Q to the N. Well, I guess N to the N. And then P, I'm not going to define it. It's a certain vector such that if you add up all the components, you get the minus the signature over 8. And it's kind of like this equivariant decomposition of negative signature over 8, but won't go into it. And let's let EK to the K unit vector. Okay, sure. Then we get the following here. So it's a little strange, right? So it breaks into two statements, and it's because we're inside of this poset, all right, and they're like multiple elements of K, right? So what it says is that for all kappa sitting inside of K of Y as sigma, all right, Q is not strictly less than P plus B0 minus kappa, right? And then we know that there exists a kappa sitting inside this set such that Q is greater than or equal to P plus E0 minus kappa. And so compare this with Manilescu's original inequality. So it's kind of nice. It's like this weird, like equivariant decomposition of Manilescu's inequality. All right. So let me tell you a little bit about the Seiberg Floor spectrum, some of the technical stuff that goes into it. All right. So if you've seen this stuff before, you'll know that Seiberg Floor spectrum is actually made metric independent by you first construct a metric dependent spectrum, and then you shift it by this correction term n of YSG, which is in general rational number, right? And that like fixes it so it's independent of the metric, right? And this is similar to the absolute rational grading on Hager floor homology. And in the equivariant case, right, the G star M equivariant spectrum SWF of Y S sigma hat is made metric independent by shifting the grading by an equivariant correction term, right? So instead of sitting inside of Q, all right, in the case where sigma hat is even, it's going to lie inside the representation ring of Z mod M tensor rationals, and then in the odd case, it's going to sit inside our Z mod 2 M tensor rationals. All right, so difficulty is kind of constructing this equivariant correction term. Roughly, what it should satisfy is that if you look at the difference of it between two different equivariant metrics, the difference is given by the equivariant spectral flow for any path of metrics between those two metrics. So whatever that means, all right, let's kind of see what this equivariant correction term looks like. All right, so for simplicity, let's restrict to the even case, right? So it's sitting inside of representation ring, Zn tend to the rationals. Now let's say gamma be a generator of Z mod M. Okay, so it's easier to look at the characters of this representation at the different elements. So the character of this at 1 is just going to be equal to the ordinary non-equivariant correction term that appears in the PIN2 theory. All right, and I want to explain what those are. For K not equal to 0, we're going to get this interesting expression. All right, so let me explain what each of these terms mean roughly. Okay, so first term is the reduced equivariant eta invariant of the Dirac operator. Essentially, this is kind of like a Riemann zeta type function that takes into account the spectrum of the Dirac operator on the boundary and also the action, the group action on it. And then the psi is just this product of trig functions, which depend, all right, so we're summing over, we look at the sigma to the k fixed point set of y, and look at sum over all components, k sub kj sitting inside of there, right? It's in general just going to be a union of knots. And for each knot, all right, psi, just some product of trig functions. And T is this kind of differential geometric invariant, torsion invariant, which captures information of G near the fixed point set. All right. Okay, so, all right, in general, this really hard to compute, right? So I won't go into it, but let me roughly give you like the lay of the land of what's going on here. All right, so if m is a power of 2, it turns out that things cancel out in the theory. We don't actually have to compute these quantities at all. Right? We can kind of cheat and just use existing computations. But on the other hand, we obtain less information from our 10-8 inequalities, right? For technical reasons, which I unfortunately can't get into. It has to do with the non-uniqueness of monomials in the WIs in the representation. But if m is odd, it turns out that our 10-8 inequalities are actually much more powerful. But in order to compute these equivariant taft invariants, we're forced to compute this like equivariant eta invariant of the Dirac operator and this like torsion invariant explicitly, which like totally sucks. But yeah, all right, so but we can try our best. All right, so some work in progress like after this set of work. All right, so try to compute these equivariant eta invariants for the Dirac operator for specifically Seifert-Fibert spaces where Zm acts by rotation in the S1 factor with respect to the usual Seifert metric, right? So a very concrete thing. All right, so for example, this is useful in the case where we think of sigma T3n as the threefold branch cover over T2n and as the n-fold branch cover over T2. All right. So in this concrete example, all right, so let's consider the threefold action on this. All right, so here's a conjecture. It's a theorem modulo 1 lemma, which is still avoiding being proved. All right, but this is what it looks like. It's absolutely disgusting. But anyway, I've got this expression in terms of like roots of unity and some invariants alpha I, beta I, gamma I, L degree of the orbifold canonical bundle, right? All depending on like these Seifert invariants, which I won't go into, but just to give you a flavor of the type of stuff that goes into calculating these invariants. All right, so that is pretty much all I have for you today. Here's an overview of all of these inequalities laid out so you can compare them. And yeah, that's all I got. Yeah, Ryan.
So as I understand, if you fix the 3 manifold, what you're saying is you're getting properties about 4 manifolds that this might bound.
Yeah.
So in the case of like branch covers of, knots and S3, you can compute something about maybe a branch cover of like pushed in Seifert surface in the 4-ball, and this tells you information about any other 4 manifold that branch cover might bound.
Yeah. Can you say that again?
So like, if you want to think about a branch cover over a knot in S3,
Right.
you can compute the thing for like a branch cover of the 4-ball over a pushed in Seifert surface, right? And then that's telling you about any possible 4 manifold that this branch cover the knot might bound. Like there might be others. I don't know what they would look like, right? But this is restricting somehow what 4 manifolds it can bound.
So I guess I'm confused about your question about like the 4-ball like genus of determining everything.
Maybe we can talk after. Yeah. One question is better form, but yeah.
Answer your equivariant question. Okay. I don't remember exactly what I said.